Hi, welcome all to the online classes. I'm Mukesh Bhardwaj. Today going to deliver a topic, diffraction in engineering physics, BTech first year. Diffraction, as we know that if we place an obstacle in front of sound source, sound is also heard behind the obstacle in its geometrical shadow region. It is possible only when the sound waves bend round the corners of the obstacle and reach the listener. The phenomena of bending of the sound wave around the corners of the obstacle is called diffraction of sound. Now, as we know that if some sort of obstacle is placed, and we even after that we hear the sound, so it comes to the conclusion that the sound is just bent around the corners and reach behind the obstacle. This is called diffraction of sound. Similarly, in the case of light also, the diffraction of light. Similarly, the outer boundary of the shadow of an obstacle is formed by light is not sharp but blurred because some part of the light bends around the corners and enters into the geometrical shadow region. If we see a vertical tube light through a parallel narrow slit made between two fringes kept in front of eyes, alternate bright and dark fringes are seen. Both these can be explained on the basis of diffractions of wave. So, this is somewhat basics of diffraction. By the earlier knowledge, we knew that in relate to the sound. Now, diffraction can be described only with a wave model. For a light, a diffraction pattern occurs when the light from an aperture is allowed to fall on a screen. The features of this diffraction pattern can be investigated under certain under certain conditions. Transfer waves with electric field vectors in all directions can be polarized in various waves. Only certain directions of electric field vectors are present in the polarized wave. Light of wavelength comparable to or larger than width uh, of a slit spreads out in all forward direction upon passing through the slit. This phenomena is called diffraction. This indicates that light spread beyond the narrow path defined by slit into regions that should be in shadow if light travel in straight lines. Diffraction pattern: a single slit placed between a distant light source and screen produces a diffraction pattern. It will have a broad, intense central band called the central maxima. The central band will be flanked by a series of narrower, less intense secondary bands called side maxima or secondary maxima. The central band will also be flanked by a series of dark bands called minima. Diffraction pattern: single slit. The diffraction pattern consists of the following: central maximum, series of secondary maxima and minima. The pattern is similar to an interference pattern. Diffraction pattern object age. This shows the upper half of the diffraction pattern formed by light from a single source passing by the edge of an opaque object. The diffraction pattern is vertical with central maximum at the bottom. So the diagrammatic representation, you just go through this to understand in a better way through the diagram. Ray optics would predict a dark spot in the center. Wave theory predicts the presence of the center spot. There is a bright spot at the center. Confirm wave theory. The circular fringes extend outward from the shadow edges. Notice the bright spot at the center. Now, Fraunhofer diffraction pattern, as there are two types of diffraction. One is the Fresnel diffraction, second is the Fraunhofer diffraction. So, a Fraunhofer diffraction pattern occurs when the rays leave the diffracting object in parallel direction. Screen very far from the slit. Could be accomplished by converging lens. As you see in the figure, incoming wave is passed through the slit and the view is screen in which we just find the maximum bright, and after that the secondary minimum, and the pattern consists of central bright fringe flanked by much weaker maximum alternating with dark fringes. Fraunhofer diffraction pattern photo. A bright fringe is seen along the axis theta equals to 0. Alternate bright and dark fringes are seen on each side. The pattern consists of central bright fringe flanked by much weaker maximum alternating with dark fringes. Diffraction versus diffraction pattern. Diffraction refers to the general behavior of a wave spreading out as they pass through a slit. A diffraction pattern is actually a misnomer that is deeply entrenched. The pattern seen on the screen is actually another interference pattern. The interference is between parts of the incidental light illuminating different regions of the slit. Single slit diffraction. The finite width of the slit is the basis of understanding Fraunhofer diffraction. According to Huygens' principle, each portion of the slit acts as a source of light waves. Therefore, light from one portion of the slit can interfere with the light from another portion. The resultant light intensity on a viewing screen depends on the direction theta. The diffraction pattern is actually interference pattern. So, we can say thus the event of banding of waves around the corners of an obstacle, that is diffraction. It is a general property of the wave. This phenomena can be observed very clearly in sound waves and radio waves, but rarely observed in light waves. In special cases when the obstacle is very small, this event can also be observed in light. The phenomena of banding of light waves around the obstacle entering into the region of geometrical shadow of the obstacle is called diffraction of light. The diffraction of light basically is observed only at the boundary of the geometrical shadow. In short, the phenomena of deviation of light from its rectangular propagation is called diffraction. Diffraction phenomena was first discovered by Grimaldi in 1665, but correct explanation of this phenomena was given by Fresnel in 1818 on the basis of Huygens wave theory. Dependence of diffraction of wave on the size of the obstacle and wavelength of the wave. Diffraction of wave depends on the following: size of the obstacle, wavelength of the wave. So, diffraction depends on the two parameters. Now, I had already told you that there are two types of diffraction. One is Fresnel diffraction and second is the Fraunhofer diffraction. So, the source of in Fresnel diffraction, the source of light or observation point are both at finite distance from the diffractor, whereas in Fraunhofer diffraction, the source of light and observer point both are effectively at infinite distance from the diffractor. In Fresnel diffraction, the incident and diffracted wave fronts are either spherical or cylindrical, wherever in Fraunhofer diffraction, the incident and the diffracted wave fronts are plane. In Fresnel diffraction, no lens or mirror is used, whereas in the Fraunhofer diffraction, diffracted light is collected by lens. In Fresnel diffraction, distance are important in this class of diffraction, and in Fraunhofer diffraction, angular inclinations are important in the class of diffraction. So, single slit diffraction analysis, all the waves are in phase as they leave the slit. Wave 1 travels farther than wave 3 by an amount equal to the path difference. So, this is a single slit diffraction. The intensity equation, the intensity can be expressed as I equals to I maximum. This formula is to be used for calculating the intensity. And finally, most of the light intensity is considered in the central maximum. The graph shows a plot of light intensity. Intensity of two slit diffraction patterns. When more than one slit is present, consideration must be made of the diffraction pattern due to individual slits, the interference due to the wave coming from the different slits. The single slit diffraction pattern will be act as envelope or two slit interference pattern. Intensity of two slit diffraction pattern equation. To determine the maximum intensity, the factor in the square brackets represent the single slit diffraction pattern. This act as an envelope. The two slit interference terms is cos square term. Intensity of two slit diffraction pattern, graph of pattern. The broken blue line is the diffraction pattern. The brown curve shows the cos square term. This term by itself would result in peaks with all same heights. The uneven heights result from the diffraction terms in the equation. To find which interference maximum coincides with the first diffraction minimum, d sine theta, d by a sine theta equals to m lambda by lambda is d by a equals to m. The condition for the first interference maximum, d sine theta equals to m lambda. The condition for the first diffraction minimum, a sine theta equals to lambda. Resolution: the ability of optical system to distinguish between closely spaced objects is limited because of the wave nature of light. If two sources are enough far enough apart to keep their central maximum from overlapping, their images can be distinguished. The images are said to be resolved. If the two sources are close together, the two central maximum overlap and the images are not resolved. ABC and ADC, we find that sin theta 1 equals to BC by AC equals to V1 delta upon AC, and sin theta 2 equals to AD by AC, V2 delta upon AC. The preceding equations can be simplified to sin theta 1 upon sin theta 2 equals to V1 by V2, but sin theta 1 upon sin theta 2 is written as N2 by N1. And so N1 and sin theta N1 equals to N2 sin theta 2. This is known as the laws of refraction, or Snell's law of refraction. Now, dispersion. So before starting to the dispersion, I will like to put some light on reflection of light from plane surfaces. Some facts: the reflection from plane surfaces obeys the following laws, which we know that. Just wait a minute. So before starting to the dispersion, I need to discuss some facts about the reflection of light from a plane surface. The reflection from a plane surface obeys the following laws. The angle of incidence equals to the angle of refraction. The incident ray, the reflected ray, and the normal all lie in the same plane. Images: a real image is one through which the rays of light actually pass and which can be formed on a screen. The virtual image is one through which the rays do not actually pass, although they appear to come from it. The image produced by a plane mirror is virtual. Its distance behind the mirror is same as the object's distance in front of it. The image is laterally inverted, that is, it is reversed left to right. The inversion of left-right symmetry is called perversion. It's called perversion. Does a plane mirror produce a virtual, perverted, and same size image? Plane mirror. I'm not talking about the concave or convex mirrors. I'm talking about the plane mirror. So the plane mirror produces a virtual, perverted, and same size image. Uh, some facts: the focal length and the radius of curvature of a plane mirror are infinite. This means the power of a plane mirror is 0. The magnification of plane mirror is 1. That is, the size of image equals to the size of the object. The left side of the object appears as the right side of the image, that is the lateral inversion or perversion. If the object moves with the speed u towards a fixed mirror, the image also moves towards the mirror with same speed. The speed of the image relative to the object in this case is 2u. If the mirror moves with the speed u towards away from the fixed object, then the image appears to move towards or away from the observer with the speed 2u. If the mirror moves away or towards an object by distance z, then the image moves away or towards the object by a distance 2d. If a mirror is rotated in the plane of incidence by an angle theta, then the reflected ray is turned through an angle 2 theta. On reflection from a plane mirror, plane mirror, a ray is deviated through an angle del. On reflection, the velocity, wavelength, and the frequency of the light does not change, but the amplitude or intensity of the reflected ray is less than that of the incident ray. Reflection from a smooth plane surface is called regular. In regular reflection, a pencil of parallel rays is reflected as a pencil of parallel rays. Reflection from rough plane surface is called irregular. In irregular reflection, a pencil of parallel rays on reflection get diffused. The twilight is caused by the diffuse reflection of the sunlight from the dust particles, water vapor, etc. The minimum size of the mirror required to see full size image of one is equal to half the height of the observer. The minimum size of the mirror required to be fixed on the wall of a room so that an observer in the middle of the room can see full image of the wall behind him is 1/3 of the height of the wall. Plane mirrors are used in optical lever, sextant, kaleidoscope, periscope, seeing round corners, dental mirrors, telescope. Reflection from a denser medium introduce a phase difference of pi. Now, inclined mirrors, number of images. Suppose two plane mirrors are inclined at an angle theta. Suppose two plane mirrors are inclined at an angle theta. Let an object is placed in front of the two mirrors. The number of images are formed due to multiple reflection on the two mirrors. The number of images formed is determined as follows. So case first, when 360 degrees is exactly divisible by theta degree. That is 360 divided by theta is an even integer. Then number of images formed is 360 divided by theta minus 1. Whatever may be the location of the object. Whatever may be the location of object. Case second, when 360 degree is exactly divisible by theta and 360 divided by theta is an odd integer. The case first is for even integer. If 360 is divided by theta and even integer come out, then number of images can be given by 360 upon theta minus 1. And if 360 divided by theta gives an odd integer, the number of images formed is 360 divided by theta minus 1 for symmetrical placements. For symmetrical placements. In case of even integer, location can be anywhere. Whatever may be the location of the object. Okay. But in case of the odd integer, the number of images is given by 360 by theta minus 1 for symmetrical placement. And if the symmetrical, unsymmetrical placement is there, then the number of images is given by 360 upon theta. Case number third, when 360 is not exactly divisible by a theta, then number of images formed is equals to integer value of n. Where n is equals to 360 divided by theta. A summary table, I just give it to you in the verbal way. Suppose if theta is 30 degree, So 360 divided by theta come out to be 12. So number of images, symmetrical placement 11, unsymmetrical placement 11, because 12 is even integer. Now if I just take for example, if I take theta equals to 120 degree, theta equals to 120 degree, then 360 divided by theta come out 360 divided by 120 give 3, that is odd. So at the symmetrical placement there will be two images, and if the unsymmetrical placement is there, then there will be three images. So this is some small review about the reflection of light at plane surfaces, or refraction of light from a plane surfaces. Now refraction at plane surfaces. So we need to summarize the some facts. Reflection and refraction. So refraction can take place without change of path. Also, when incidence ray is equal to refracted equals to 0. The deviation of incident ray when it is refracted is by an angle del is given as I minus R mod. On refraction, the frequency of light does not change. This is very important. On refraction, the frequency of light does not change, but both the wavelength and the velocity changes. So the wavelength and the velocity will change. So velocity can be find it out by c by mu, and the wavelength can be in a medium, can be find out by wavelength in vacuum upon mu, where mu is the absolute refractive index of the medium. C is the velocity of light in the vacuum, and the V is the velocity of light in the medium. The symbol for refractive index has been changed from n to mu. For air, for some mediums, like for air, refractive index is 1, which we had already discussed. Therefore, when light passes from air into any transparent solid or liquid, the refractive index is always greater than 1. The refractive index of medium 2 with respect to medium 1 is mu 2 equals to first mu 2 equals to mu 2 upon mu 1. A medium 2 is said to be optical denser in comparison to medium 1 if mu 2 is greater than mu 1. Wavelength of color of light, wavelength or color of light and temperature of the medium. Refractive index decreases with increase in temperature. Refractive index does not depend on the angle of incidence. When the medium is same on both the side of a glass slab, then the deviation of the emergent ray is 0. That is, the emergent ray goes parallel to the incident ray. The refractive index of glass with respect to water can be expressed as 9 by 8. So these are the some fundamentals and some facts related to the refraction and the reflection. Now dispersion. Dispersion for a given material, the index of diffraction varies with the wavelength of the light passing through the material. The dependence of an on wavelength is called dispersion. This dependence of n, that is refractive index, index of refraction. So the dependence of refractive index on wavelength is called dispersion. Snell's law indicates light of different wavelengths is bent at different angles when incident on a refracting material. Next, Variation of index of refraction with wavelength. The index of refraction for material generally decreases with increasing wavelength. Violet light bends more than red light when passing into refractive material. Refraction in a prism. Since all the colors have different angles of deviation, white light will spread out into a spectrum. Violet deviates the most, red deviates the least, the remaining colors are in between. The colors in the refracted beam are separated because dispersion in the prism causes different wavelengths of light to be refracted through different angles. The rainbow. A ray of light strikes at a ray of light strikes a drop of water in the atmosphere. It undergoes both reflection and refraction. First, refraction at the front of the drop. Violet light will deviate the most, red light will deviate the least. At the back surface of the light is reflected. It is refracted again as it returns to the front surface and moves into the air. The ray leaves the drop at the various angles. The angle between the white light and the most intense violet ray is 40 degrees. The angle between the white light and the most intense red ray is 42 degrees. So the pictorial representation, the violet light refracts through larger angle than the red light as shown. While observing the rainbow, the highest intensity light traveling from higher raindrops towards the eye of the observer is red, whereas the most intense light from the lower drop is violet. If a raindrop high in the sky is observed, the red ray is seen. A drop lower in the sky would direct violet light to the observer. The other colors of the spectrum lie in between the red and the violet. Double rainbow. Some of the time we had seen that there are the two rainbows seen in the sky during the rainy season. The secondary rainbow is fainter than the primary. The colors are reversed. The colors are reversed. The secondary rainbow arises from the light that makes two reflections and from the interior surface before exiting the raindrop. Higher order rainbows are possible, but their intensity is low. Total internal reflection. It is a phenomena called total internal reflection can occur when light is directed from a medium having a given index of refraction toward one having a lower index of refraction. Possible direction of the beam are indicated by the ray numbered 1 through 5. In the pictorial representation, as you see that the possible direction of the beam are indicated from ray 1 to 5. 1, 2, 3, 4, 5. The refracted rays are bent away from the normal since n1 is greater than n2. Critical angle. This is a particular angle of incidence that will result in an angle of refraction of 90 degree. This angle of incidence is called the critical angle, theta c. Sin theta c equals to n2 upon n1. For angles of incidence greater than the critical angle, the beam is entirely reflected at the boundary. This ray obeys the laws of reflection at the boundary. Total internal reflection occurs only when light is directed from the medium of a given index of refraction towards a medium of lower index of refraction. Fiber optics, an application of internal reflection, that is, the basic working principle of fiber optics is on the basis of total internal reflection. Plastic or glass rods are used to pipe light from one place to another. Applications including medical examination of internal organs, telecommunication. This is the construction detail of an optical fiber. The transparent core is surrounded by cladding. The cladding has a lower refractive index than the core. This allows the light in the core to experience total internal reflection. The combination is surrounded by the jacket. A flexible light pipe is called a optical fiber. A bundle of parallel fiber shown can be used to construct an optical transmission line. So this is the wave versus particle nature, Huygens principle and diffraction we had seen. Huygens principle can now explain the law of refraction. We had already covered. These are the some pictorial representation. Why the mirage are seen to us in a sunny hot days? Highway mirages are due to gradually changing index of refraction in heated air. So mirage appears to be seen just to gradually changing index of refraction. So this is the interference Young double slit experiment. We will start this Young double slit experiment just a little bit later. Before to that, I'd like to discuss dispersion overview. What do you mean by the dispersion? Uh, that is, when we had seen that there is a refraction through a prism. The refraction of monochromatic light through a prism is we had seen in the figure in the previous slides. The two refracting surfaces are shown over there. The angle between these two refracting surfaces is known as the prism angle. Uh, the angle of incidence and the angle of emergence is E, which we had seen in the diagram in the previous slide. And if mu is the refractive index of the material of the prism, then mu is given by sin I upon sin R is equals to sin E upon sin R2. The angle between the incident ray and the emergent ray is known as the angle of deviation, that is delta, which we had also discussed. For refraction through a prism, it is found that I plus E is equals to A plus delta. R1 plus R2 is equals to A. It's some mathematical concepts which you can go through some reference books, and in that reference book you find some relationship. So dispersion, the separation of white light into its component colors, is called dispersion. Dispersion is nothing. Dispersion, the definition of dispersion is that separation of white light into component colors is called dispersion. The band of colors is known as spectrum. The spectrum of visible light contains Vibgyor. Everyone is very much familiar about or aware about Vibgyor. Stands for violet, indigo, blue, green, yellow, orange, and red. Dispersion occurs because the index of refraction is not strictly a constant for a particular material, but rather varies slightly with wavelength. For example, we had already discussed that index of refraction of a crown glass for red light is 1.51, whereas for violet light it is about 1.53. In case of a prism, the dispersion is most pronounced because the two refracting surfaces are inclined. For small angle prism, a mathematical formula, that is delta red is equals to mu red minus 1 into A, delta violet is equals to mu violet minus 1 into A. Uh, so some facts about the spectrum, because the band of colors is known as the spectrum, which is obtained by the dispersion, that is the white separation of white light into the components color is known as dispersion, and the band of colors is known as the spectrum. So some fact about the spectrums are: a spectrum in which the constant constituent colors have sharp boundaries and are distinctly visible is known as pure spectrum. Impure spectrum: in this type of spectrum, various colors mix. To obtain the pure spectrum, one uses the following arrangements: band spectra, absorption spectra, Fraunhofer lines, and fluorescence. It is a process by which body absorbs short wavelengths of light and subsequently emit longer wavelengths. So this is all about the dispersion. Now in the next lecture, we will start with interference, refraction, and diffraction. And before ending to this lecture, I would like to discuss some questions. When a pebble is dropped into a pond of still water, what happens? What happens? The pebble moves. When a pebble is dropped into a pond of still water, what happens? A particle moves, wave moves, the pebble moves, water moves. A wave moves. The perfect answer is a wave moves. Mechanical waves are called elastic waves. So mechanical waves are not called elastic waves. The statement is false. What are the essential properties a medium must possess for the propagation of mechanical waves? So, what are the essential properties, or which of the essential properties a medium must possess for the propagation of mechanical waves? Stable pressure, maximum friction, constant temperature, minimum friction. Maximum friction or minimum friction? What are the essential properties of a medium must possess for the propagation of mechanical wave? Obviously, minimum friction is needed to be provided for smooth propagating of the mechanical waves. Now, sound travels through a gas under which of the following condition? Isothermal condition, non-isothermal condition, adiabatic condition, transverse condition. So sound travels through a gas under which of the following condition? Through a adiabatic condition. What kind of wave is formed in organ pipes? Mechanical waves. A wave transmit momentum cannot or can't it transfer angular momentum? No. What is the most Fundamental property of wave: temperature, pressure, frequency, wavelength. Almost all are the properties of wave, but the fundamental property is the frequency. Fundamental property is the frequency. Which among the following is not a suitable phenomena to establish that light is a wave motion? Light is a wave motion. Interference, diffraction, reflection, polarization. So, reflection is not a suitable phenomena to establish that light is a wave motion. Interference is the suitable phenomena to establish that light is a wave motion. Diffraction is same and the polarization. Now, this numerical, the optical path of monochromatic light is same if we travel 2 centimeter thickness of glass or 2.25 centimeter thickness of water. If the refractive index of water is 1.33, what is the refractive index of the glass? So the parameters are with you. Put in the formula and get out the refractive index using the Snell's law. Identify the condition for which it is not necessary for two light waves to be coherent. The two waves must be continuous. The two waves should be of the same frequency of the wavelength. They should have a constant or zero phase difference. The two light source should be narrow. So this two light source should be narrow is not necessary for two light waves to be coherent. So this is all about the wave nature of light, refraction, reflection, dispersion. Okay. A light wave enter from air into glass. How will the energy of the wave be affected? So energy of the wave decreases. A light wave enter from air into glass. How will the frequency of the wave be affected? It remains unchanged. Which among the following is an example of coherent source? Fluorescent tube, LED light, lasers, tungsten filament lamps. So laser is the example of coherent sources. So these are the some questionnaires related to the wave nature of light. Now in the next class, we are going to start with interference, Young's double slit experiment, and further some more topics in continuation to the interference. Thank you. Thank you to all. Thank you.